Okay, we've looked at recursive functions and we've looked at recursive sequences. In this video, we're going to look at recursive algorithms. Right? Now, a recursive algorithm works in much the same way recursive functions and sequences do, and we're going to use itself in its definition. So a recursive algorithm is going to call itself, right, to solve the problem. So you need to solve, or write a recursive algorithm, you're going to call the algorithm within itself on a smaller input set and perform the same task on a smaller problem and keep making that problem smaller and smaller until you've reached a point where you can stop, much like we did with the recursive functions. We're going to take a look at a very common operation, one that we did with recursive functions, the idea of raising a number to a power. So in this algorithm here, power an, we're going to let a be the base. And n be the exponent. Okay. And we're just going to make an assumption here that they're both integers, just to keep things cleaner here. Certainly a could be a real number. Raising a real number to an integer power isn't a problem, but if the n becomes anything other than an integer, then we would have a problem. Again, I'm going to keep working on trying to fix the pen issue, but it's just not working that well, and my finger can only do so much on the computer I have at home. So hopefully you can still read my handwriting enough for it to be effective. Now, the key is that every time you want to raise a number to a power, if you wanted to raise, like, let's say 4 to the 5th power, right, you could think about that as 4 to the 4th power, a lot of 4s I realize, times 4, right? And then 4 to the 4th power is really 4 to the 3rd power times 4, right? This is what we did before in the recursive function example. So the recursive step, right, with the definition is to take what you have, right, with the smaller example and multiply it by the base one more time, right? So the idea is you're going to take the base, raise it to the n minus first, or 1 less power, and then multiply it by a. So every time you call this algorithm with n, you're going to store that power, the base raised to the nth power is going to be the same as the base raised to the n minus first power times the base, right? And multiplying by that base is that one extra multiplier that brings you back up to n. So then when you try to figure out an minus 1, you're going to take an minus 2 times a, and you're going to keep doing this until eventually you stop. And I think the hardest part with writing recursive algorithms is trying to figure out when do you stop. Even though the stopping line here comes first, I think it's really more important that you sort of focus on what the recursive step is. How do you get from one step to the next? Now, in this course, we're not writing recursive algorithms. We're just learning how to follow them. So that makes things a little bit simpler. But eventually, especially those of you that are computer science majors, you will be writing this. So all I would really ask you to do here is, if I gave you an algorithm like this, ask you to follow it for a specific value. First, I just want to go over where it comes from. So when do we stop multiplying by a power less, right? We stop, the base case for exponentiation is that when you reach 0, right, anything raised to the 0 power is 1. Now, in theory, you could stop at a to the 1 being a, right? But then that doesn't allow 0 as an input to this function. So the most general base case is to let a to the 0 equal 1, and that's what this line here says. So when you actually hit that value, that's when you'll stop calling the recursive values and then you'll start feeding the values back in. So if you were going to trace power, let me try that because it's writing. Let me see if I can get it a little bit neater. Power, let's say 3, 4, right? First thing we would do is, right, understand that the a is 3 and the n is 4, right? So the first thing we're going to do when we trace this code So we're going to ask ourselves, is 4 equal to 0? Right? The answer is no. So we're going to let power 3 comma 4. This is just not working. 3 comma 4 equal, difficult. It's going to be power of 3 comma 3 times the base 3. Okay, now is the exponent 3 equal to 0? Again, the answer is no. So we're going to let power of 3 comma 3 get to the recursive step. Power 3 comma 2, right, reducing by 1 times 3. So now the n is 2. Is 2 equal to 0? I should pick the smaller exponent, but this will help give you some good experience to see it traced a little bit longer as long as my pen holds up here. Power 3 comma 2. Every time you haven't reached the end, you have to do this one more time. 3, 1 equals 0. No. So power 3 comma 1 is going to equal power of 3 comma 0 times 3. 0 equal to 0. Okay, so is 0 equal to 0 finally? The answer becomes yes. So power of 3 comma 0 gets 1, right? And now we're basically just performing the recursive function like we did in the previous example. This one gets fed into 3 comma 0, so 1 times 3 is 3. That 3 gets fed into 3 times 1, so 3 times 3 becomes 9. And that 9 gets fed in here, and 9 times 3 becomes 27. Right? And then that 27 gets fed in here. And 27 times 3 is 81, right? And that's the final answer. That's what 3 to the 4th power is. So tracing the recursive algorithm is a lot like doing a recursive function. You're not going to be asked to write a recursive algorithm in a particular section. You would just be asked to trace one. Okay? So we can try one more quick one. This is just a made-up function. Foo is sort of a generic name for a random origin of it. I don't want to take a lot of video time doing that, explaining that, but let's say I asked you in this case to trace and calculate foo comma 3. We'll do a shorter example this time. So for foo of 3, right, we're going to start basically here with n equals 3. Right, this function only has one input. Does 3 equal 1? Oops, finger was writing faster than my mouth there. Does 3 equal 1? The answer is no. So returning foo of 3, right, which is sitting around waiting for the answer, is going to be 4 times foo of 2. Right? Does 2 equal 1? Right? The answer is no. So foo of 2 equals 4 times foo of 1. Does 1 equal 1? Right, the answer is yes. So foo of 1 gets the value 6. Right? Now we just kind of funnel our answer up. 4 times 6 is 24. This 24 goes into foo of 2. 4 times 24 is 96, and that'll be the final answer. So the word trace, right, means not just give me the answer, but show me all the steps involved. That includes all the comparisons. It shows that you can use the algorithm in the right way, doing all the checks and then calculating all the values. Right, so keep it pretty simple, just to show the basic point. But recursive algorithms have a big importance